problem that gave students the most trouble this week seems to be problem 2 in the written assignment number 7. So I've copied it here so I can talk through it. So you're asked to determine if this collection of polynomials, so this collection of polynomials in P3 is a basis for P3. That's where P3 is the collection of all polynomials of degree 3 or lower. So any polynomial in P3 has this form. It's something times t cubed plus something times t squared plus something times t to the first, and then plus possibly some constant. So I'm going to write d times 1 here. So what I've written here for p of t is actually a linear combination of the polynomials t cubed, t squared, t, and just any constant, but I've chosen 1 here. You could put any number there. Now this forms a basis. This would be the standard basis for P3. Just like in the notes, you might have seen the standard basis for, say, P2. So the polynomials degree 2 or lower would be t squared, t to the first, and 1. Okay, so this is a side note here. Since here I have a basis for P3 that contains 4 polynomials, 4 vectors, vectors in quotations here, then I know that the dimension of P3 is 4 because there's four vectors in that collection. Now note that the set that I gave you only has 3 polynomials. So it's not possible to have a basis, another basis for P3 that has fewer vectors in it. And so the theorem that you could refer to here is theorem 4.5.1 in the notes that says if you have one basis for a vector space that has n vectors, then every basis for that vector space must have n vectors. That any basis for a certain vector space has to have the same number of vectors. So the theorem that many students referred to, theorem 4.5.2, says if you have a vector space with dimension n and you have a collection of n vectors, then you know it's a basis if you just prove that they're linearly independent or just prove that they span the vector space. But the problem with that, so the problem with referring to theorem 4.5.2 is that if part. If you have a vector space, let me move this. So if a vector space V, let's say, has dimension n, then a collection of n vectors, I should have copied it onto the screen here, but a collection of n vectors is a basis if you just prove one of the following: if that collection is linearly independent, or if the vector spans the vector space V. But what you're missing is this collection of n vectors. The dimension of P3, like I said up here, is 4, and you don't have 4 vectors. So you're missing the whole beginning part of this theorem. That's why you can't apply that one. So the correct answer for number 2 is to point out that the dimension of P3 is 4 and that you were only given 3 vectors, so there's no way it's a basis.